All right, check out the flower power today. Mrs. Smith, real hippie, if you know her. Yep, big hippie teacher. Yeah, she made these notes. I added some slides in, but here we go. 11.2, talking about probability, theoretical and experimental probability. We'll get up through geometric, and then I will leave geometric. So you'll have geometric tomorrow, brand new. So we'll leave that for sure. But let's get started talking about what does it mean. Probability is really the likelihood of something happening, and it can be represented in kind of basically three ways: as a number between 0 and 1, as a fraction, like a ratio, and it has to, of course, be between 0 and 1 still, and then a percent between 0 and 100. So 0 would mean that some likelihood of something happening would be impossible. And then 50% would be like as likely as not, and 100 or 1 would be certain. Okay, so probability is a number between 0 and 1. Some definitions and terms from the book. Just kind of talked about that. Some new lingo in here would be an outcome. So each possible result of a probability experiment or situation is an outcome. The sample space is the set of all those possible outcomes, and an event, that's what we say, like an event, is a outcome or like a set of outcomes. Like, for example, an event might be, if we're looking at this number cube, which is kind of dumb, they call it a number cube. It's actually a die. Yeah, they don't want you to be going out and being all of a sudden, number cube, let's go gamble, woohoo, and then hit the town, you know. So like, I'll just call it a die. I'll roll the number cubes and call it a die. And anyway, so let's say the event would be rolling an even number. That's an event. Rolling an even. That's an event. You could calculate the probability of that event. What would the probability of rolling an even number be? 1/2, right? There's half of them are evens, 2, 4, and 6. So the sample space is all the possible outcomes. An event is usually what you're talking about happening. So in this case, an event would be part of the outcomes, 1 or 2, 4, and 6. Spinning a spinner, same thing. Outcomes, red, blue, green, yellow. It's a sample space. So knowing what those terms, sample space, events, outcomes, are talking about. What happened here? Okay. This is a neat little spinner thing. You can, yeah, it actually works. Watch this. So the sample space for the spinner, this was just on the previous page, but if you write a sample space, we usually use some curly braces, and then you got, actually you said blue. It's not blue, it's purple. Someone said blue earlier, and but purple, green, orange, red. Those 4 possibilities. Someone might argue the line, right? Ooh, is the line. So orange, the line, but we'll just stick with those 4. Those are the outcomes that make up the sample space. The outcome shown right now is orange. So anyway, just understanding what those terms mean. This spinner actually works. Watch how neat this is. Whoops, I can't be on that though. Whoops. Oh, all right. Well, this is taking tons of fun class time. Oh, never mind. I got it. Whoa! Take it easy. What's going on here, Gary? Yeah, you actually just have to push it. Yoo-hoo! All right, you want to make a guess? Let's go until it lands on a line. Come on, let's get. Ooh, that one was really fast. Whoa, one cranked on that one. I don't know if it's truly random. Anyway, so that's neat. Probability of flipping one, or sample space of flipping one coin. Heads, tails. Ooh, that one was tricky. I had to talk to Tuomas, the Finnish exchange student, about heads tails. I asked him, I was like, "Do you guys have heads tails on your coins?" And he said, "No, we have number side and then like something else." So it's like maybe number side or no number side on their coin. Yeah, I don't know. Then I talked to him about the president's heads, and we call it heads. And then I don't know why we call the other one tails. No, it's not. I don't think you know either. Outcome shown here, heads. If you flip two coins, what's the sample space for two coins? You could have heads, heads. You could have heads, tails. You could have tails, heads, or tails, tails. In this case, it is outcome shown as heads, tails. No, they don't flip. I already tried. I know that would have been cool. All right, so that's sample space. You'll be asked to write sample space. Sometimes they're more difficult than others. Some sample spaces can be really tricky. Like I might ask you to write the sample space for all the possible Powerball tickets. Yeah, like you couldn't do that, right? I mean, it'd take you forever. Okay, so when you're calculating probabilities, we are going to be using to calculate the size of sample spaces, because when you calculate a probability, you need that number, and that's where we'll be using what we did in 11.1 with our counting stuff. Anywho, from the book again, you can estimate probability using data or an experiment sometimes. So some probabilities you can't just calculate like you can with a coin flip or a dice, right? So actually, I'm going to jump ahead to talk about that theoretical before that. So I want to go. This is what we just had up, was like more of theoretical probability stuff. So some events are there's like an equally likelihood of them happening. Like a coin flip, it's pretty much a 50-50, right? Um, rolling a dice, it's pretty much a 1 in 6 chance you're going to get a 1, 2, 3, 4, 5, or 6, okay? So some probabilities, when you calculate them, are more based on like a theory of the event being fair. And so like this would be more like if you're playing card game or like casino games, that type of stuff, or like a lottery, where there's equally likely outcomes in theory, right? The trick on that is that you have to play those games like an infinite amount of times for everything to be even, because sometimes you could go on like a hot streak, and then all of a sudden you think, oh, I got this thing figured out, or a cold streak. Yeah. Anyhow, so when you calculate the probability of some event using a theoretical probability, that would be your number of favorable outcomes, whatever you're trying to calculate, divided by the total number of outcomes in the sample space. So that's more of a theoretical. Let's start there. Flipping a coin. So let's just talk about, let's say if we had a coin flip, it's common to talk about that. What's the sample space for flipping 3 coins? Okay, this is one that's not terrible to write out. So we'll write this out. Heads, 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 tails, heads. Let's flip the next two and go tails, heads, and heads, tails, tails. Right, so when heads, the first coin is flipped heads, then the last two could either be heads, 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 tails, tails, heads, or tails, tails. Sort of. Let me talk about that in a minute here. What if the first coin was tails? Then you could have tails, heads, heads. Basically, you'd have the 4 same outcomes with the last 2 coins, except for tails as a starter. So we have tails, heads, heads. We have tails, heads, tails. We have tails, tails, heads, or we have tails, tails, tails. The question was, and this kind of pertains to our question up here, getting 2 heads and 1 tail. So what's the probability of heads twice and tails once, right? Okay, well, That is true that this has heads, heads, tails satisfies, heads, tails, heads satisfies, and tails, heads, heads satisfies. So like your question was, wait a minute, isn't heads, heads, tails the same as heads, tails, heads? Kind of. I mean, it's actually a different way that the coins can fall. But if your criteria is, I want to know what's the probability of getting two heads, then you can't really differentiate between these three outcomes. So it does get a little kind of murky there, kind of confusing. I get it, but they are separate outcomes. But in this case, we count them as the same for getting two heads and one tail. So this probability would be 3/8, right? Probability of getting all tails, there's only one way to do that. So the probability of 3 tails is 1/8. Right, so some probabilities, theoretical probabilities, you can just calculate as the number of favorable outcomes divided by total number of outcomes. Here's another one. Take all the letters in the word probable, cut them out, put them on a little piece of paper. What's the probability you pick a vowel? Well, or a consonant? How many consonants are there? I believe there's 5. And how many vowels? 3. O, A, and E. So out of the total 8 letters, what's the probability of picking a consonant? Maybe 5 out of 8. Makes sense? So you'd have to be a little careful here to calculate, like maybe you miscounted. Maybe you just counted B as 1 letter and it was out of 7. I mean, that's the only way I could really see maybe goofing this up. But there's 2 B's, so you actually have 2 chances. You have 1 extra chance of getting it, so you have to go out of 5 out of 8. Let's go back now to experimental probability. Yeah. Okay, some probabilities you can't really calculate just in theory. You have to do it based on some sort of experiment with trials, or I guess you could call that like a statistics-based probability. So like my example of this, and all these markers are now all over the place because Cole Stanchina threw them all over the place. Thanks, Cole. So yeah. So my thing is, what's the probability of me kicking this marker in that can over there? All right? What's the probability of me kicking this marker in that can over there? Though, good, that's a good answer. You can't, there's no theoretical probability. It's not like flipping a coin. It's not like, oh, it's 50. Some people think, though, they kind of go, well, either it goes in or it doesn't go in. It's 50%. No, that's not really how it works. You have to basically generate some statistics or an experiment, right? So I've actually done this 387 times over the last few years as I've been keeping track of this, and I made it 1 time. So, and I've never really made it on air either, so this would be pretty epic, as Dave would say. Yeah, so in slides, it's harder with slides, but let's just see. So, that was that hurt. That was way off. Closer. Heads up. Whoa! That was a perfect spiral. So, with the slides, it's hard. If you couldn't see that at home, but that was atrocious. I didn't even come close. So now that was another 8 markers, I think. So now I'm up to 1 in 395. Pretty low probability. Not a lot of action, but the suspense of it going in would be epic, as Dave would say. So anyway, I pick up these markers here. So some probabilities are more are not able to be calculated just in theory. So that would be an experimental probability. That would be the number of times the event occurs over a total number of trials in the experiment, or at bats in baseball, or free throw percentage in basketball. How many free throws have you made over how many you've taken, stuff like that. Okay, question. Okay, this is some lame math book question. Let's do an experiment with a spinner and see what's the probability of spinning a 4. I don't know, maybe they want to see if the spinner's bias. Maybe it's not lame. Yeah, maybe it's a trick spinner and we want to check. Maybe it's a really smart math book question. So they did a little 50-50 trial experiment and found that spinning a 4 was likely 14 out of 50 times. So 14 out of 50 times, that's about 1/4, isn't it? 1/4 of 50 is what, like 12.5? So I'd say it's pretty close to fair in that regard. Probably not so fair on the 1, but that can be represented as 7/25 as a lowest fraction, or 28% as a percentage, or 0.28 as a decimal, right? Spinning a number greater than 2, now we're combining some outcomes. So our event would be spinning a 3 or a 4. So the probability of a 3 or 4 is going to be 33/50ths. Yeah, yep, I got 50 by adding up all the trials or occurrences. Sure. So 33 is 66%. So if it was fair, it should be more around 50%, right? Okay. What's the probability I can throw this marker in that can over there? All right, this is a little more fun, eh? I'll throw this marker in that can from downtown. Ooh! Ooh! Oh! Oh! All right. Well, I didn't make it. I wasn't an epic hero today. So that was too bad. You all done, boss? All right. Next slide. We already talked about all this. So I think that's where we're going to stop here. Let me just double check. Oh, no. One more thing. The complement strategy. You need a pass back? Okay. So sometimes when you're counting up the number of ways something can happen, it's a lot easier to count up the ways that it can't happen and then subtract from 1. Okay. So the thing that you need to know is when you are calculating probabilities, the probability of something happening and the probability of that something not happening has to add up to 100% or 1. Okay? All right, so therefore, because of that, you can use the complement and subtract. If you want to find the probability of not E, or the event not happening, you can do that by subtracting 1 minus, or subtracting the event from 1. So the probability of not E is equal to 1 minus the probability of E. Okay, and I'll give you just a little hint on this. This will come up a little bit later in the chapter, but the probability of at least 1, if you're trying to figure out, what's the probability of at least one thing, 1 heart or something? Maybe it's a deck of cards. Probability of a hand having at least 1 heart. That's a kind of a pain to calculate all the different ways you can have. You could have 1 heart in your hand, or 2 hearts in your hand, or 3 hearts in your hand. And it's kind of annoying to add all that stuff up. So it's actually a lot easier to do 1 minus the probability of none. So then all you have to calculate is the probability of no hearts in the hand, and it just becomes easier sometimes as a strategy to calculate rather than doing the actual event itself. Okay, so I'm going to stop there, 20 minutes, and then Jackie will pick up tomorrow, right? Over and out.